The following is the video solution from JSDT Solutions. Question 9 says, in the diagram, ABCD is a cyclic quadrilateral and O is the center of the circle. Use the diagram above to prove the theorem, which states that the opposite angles of a cyclic quad add up to 180 degrees. Then prove that angle B plus angle D is equal to 180 degrees. Okay, so that's our focus. We need to show that angle B plus angle D is equal to 180 degrees. Okay, so to prove this theorem, you first start off by drawing a line from the center to the circumference, or a radius at OA, and then a radius at OC, okay, from O to C. And just ensure that you tell them any constructions that you have made. Okay, so draw OA and OC. And now we're going to go ahead and name this angle O1, and this is angle O2. You see that the angle at the center, we're going to use this theorem that we know about the angle at the center and its relationship with the angle at the circumference, as long as they are supported by the same chord or arc. Now, in this situation, angle O1, right, it's supported by this arc AC, right? But as you can see, it's the shorter arc to this arc AC. So it's supported by this arc AC, and we can also see that angle B at the circumference is also supported by that same arc. So the angle at the center is twice the size of the angle at the circumference, as long as they are supported by the same arc or chord. So we'll go ahead and tell them that angle O1 is twice the size of angle B, and then put down our reason, okay? And now we can also see the same relationship with this angle O2. Okay, so this is twice the size of this angle at the circumference. But we can also see that angle O2, right, it's supported by this arc AC. Okay, so that's a different arc. They may have the same name, but they're not the same. As you can see, they have different sizes. So this would be the major arc. It's the bigger one. So this arc is supporting angle O2 at the center, but it's also supporting angle D at the circumference. So it means that angle O2 is twice the size of angle D. Okay, so let's just put that down. We don't really need those markings. So we can tell them that angle O2 is twice the size of angle D, and it's for the same reason. Okay, now what do you notice about angle O1 and angle O2? They're both at the center. So if you added angle O1, take angle O1 and add it with angle O2, do you see that they create a full revolution, okay? Those angles will add up to 360 degrees. So we can just show them angle O1 plus angle O2 is equal to 360 degrees, because these are angles that lie around the same point, okay? Angles around the same point add up to 360 degrees. Okay, so there's our reason. And now, in place of angle O1 and angle O2, we can substitute what they are equal to. Our focus is on angle B and angle D. So angle O1 is equal to 2 angle B plus angle O2, which is 2 angle D, and this is equal to 360 degrees. So now, to find out the value of angle B plus angle D, you see that we have a common factor of 2 all across, and we can just divide both hand sides of this equation by 2. And so therefore, this concludes that angle B plus angle D is finally equal to 180 degrees. And that's how we prove this theorem. Moving on to the next question. Question 9.2 says, in the diagram below, O is the center of the circle with a reflex angle of 230 degrees. P, Q, R, and S are points on the circumference of the circle with chord SR extended to point T. And then they tell us that QRT is 85 degrees and OPS is 20 degrees. So this angle over here. And we are told to calculate the magnitude of the following angles. So we just need to find the sizes, okay? The size of the following angles. And the first angle that we have is angle S. So let's look at where angle S is and then compare it to what we have. It is at the circumference. And immediately we can also see there's an angle at the center. They're using the theorem that they used above, okay, for this proof. Do you see how this angle is supported by this arc PR. And the angle at the center is also supported by PR. So it means that this angle 230 degrees is twice the size of angle S. So you can actually just write it like this, that angle, well, did they name it? Not really, they just called it a reflex angle. But if it is twice the size, then this is the bigger angle, that's the smaller angle. So we'll know that angle S is going to be half of whatever 230 degrees is. And we'll put down our reason because of the angle at the center is twice the angle at the circumference supported by the same arc, or chord, of course. So that concludes that angle S2 is equal to 115 degrees. Okay, moving on to the next question. Question 9.2.2 asks us to find the size of angle Q. And as we can see, you see where angle Q is? Right opposite angle S. Okay, so using the theorem above, okay, that we just proved, but the other one was using a theorem that we needed to use to prove this. So this is 115 degrees. It's always good to write down the angles that you find. And now we can find angle Q. So opposite angles of a cyclic quad add up to 180 degrees. Okay, these lie on the circumference of the circle. So we have a cyclic quad here. And so we can just say that angle Q is equal to, and we'll say 180 degrees minus 115 degrees. So angle Q is equal to, that is going to be 70 minus 5, which is 65 degrees. Okay, so this is our answer. And then we should just also put the reason. So that was because of the opposite angles of a cyclic quad add up to 180 degrees. Okay, and that is our answer. Moving on to the next question. Question 9.2.3 says we need to find the size of angle P1. So looking at angle P1, it's way over here. So you see that together, this is now the angle that is the interior opposite angle. And we have an exterior angle of 85 degrees. So the exterior angle of a cyclic quad is equal to the opposite interior angle. So when we add these two together, they should give us 85 degrees. Okay, so that is 65 as well. So we'll say angle P1 is equal to 85 degrees minus that 20 degrees. So angle P1 is equal to 65 degrees. And the reason was because of the exterior angle of a cyclic quad. Okay, so that is our answer. And we can also just make sure that we put that down so we know that angle P1 is equal to 65 degrees. And moving on to the next question. Question 9.3 says, in the diagram, PQRS is a cyclic quadrilateral. And we have QA intersects SR at point A. And angle SAQ is 130 degrees. And we are also told that angle AQR is 20 degrees. And the question is to calculate, given reasons, the size of angle P. So this angle over here. How do we find that? Now, don't go start finding random things, because if you do that, you end up wasting time. Let's create a way or a strategy to find angle P. So because angle P is at the circumference and we have a cyclic quad, we can focus on using the opposite angles of the cyclic quad. So it means that in order to find angle P, we need angle R. So how do we find angle R? We can find angle R because do you see that we have this triangle over here? And this triangle has an exterior angle, 130 degrees. We know that the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So that's how we'll find angle R. So to find angle R, we can just say angle R is equal to, and we're going to take that 130 degrees minus 20 degrees, because when we add those two angles inside, they give us the exterior angle. And this is because of the exterior angle of a triangle. And so angle R is equal to 110 degrees. So we know now that this is 110. And now how do we find angle P? We know that the opposite angles of a cyclic quad add up to 180 degrees. So it means that to find angle P, we simply say angle P is equal to 180 degrees minus 110 degrees. And that is because of the opposite angles of a cyclic quad. And so therefore, angle P is equal to 70 degrees. And that is our answer. And that is it for question 9.